Good day. Welcome to lesson 6. Today we will be continuing with the second part of our unit, data structure in GIS. If you recall our lesson 5, we began our discussion on data structures where we focused a lot on vector data structures. So before we move on, I just want to make sure that you recall the definition of data structure. So if you recall, data structure in GIS refers to the way in which the data is stored on a computer for the purpose of reconstructing those models, whether the model is vector or raster data models. Okay, so that is what we had focused on in lesson 5, and today we continue with this topic and we look a bit more at data structure with regards to raster data. So before we move on to the raster data structure, let's recap a little bit about some of the characteristics of the raster data model. So we all know that the raster data model represents our data in a series of cells, and each of those cells will carry a value. So when we talk about raster data and we talk about cells, one of the things that we would be most concerned with would be pixel size. So what are pixels? A pixel is the size of the cell or the picture element, that's what we refer to as pixel, that defines a level of spatial detail. In other words, resolution. So this term resolution is not new to you, so we are just reinforcing resolution or spatial detail. So all variation within the pixels can be lost at times, sorry, not at times, but because of the way the data is represented. If you have any differences, no matter how small or how big the differences are that fall within the boundaries of that one cell, we are not able to represent it. So we say that we cannot distinguish minor variations within the cell that are less than half the cell or the pixel size. I think this is a comment we would have made in a previous lesson. So now let's talk about assignment scheme. So the assignment scheme, this refers to some of the methods that would be used to assign a value to the cells. Okay? So the value of the cell may be assigned according to any of the following methods. 1. You may choose to use the average of all your values of the features falling within the cell. For example, if you're talking about a particular type of tree or forest, within a cell you may find that you have let's say 100 pine trees, for example. So you can use that number and say, all right, the average of the greatest average would be the pine trees. You may have some others that fall within there, but you use the one that has the greatest average. Okay. The next method you may choose to use, you may look at the total of the values. So you say, all right, I have 100 pine trees, my value for that cell will be 100. Additionally, another method you may look at would be using the most common value or mode in the cell. So you have different forest tree types within that cell. You count the one with the greatest number of occurrences within the cell and you assign that value. Alright. Additionally, you may choose to go with the value that is found at the geographic center of the cell. So this is what becomes important at this point here. For this method, you're looking at what occurs at the geographic center. You're not concerned about the features that occur the most in that cell or the total or anything of that kind. You're interested in the geographic center. So those are some of the methods that can be used. Typically you would find that the method that may be most often used might be the third one, the most common value occurring in the cell. So as you recall, when we represent features using the raster data model, features are not, they're not well represented. They tend to be irregular, particularly around the boundaries. So they don't represent true size of the feature or true shape of the feature very well. Lines are jagged in appearance. So here we have our representation where we see the transition from vector to raster. So this is our vector representation. You see our nice smooth lines. Once this has been assigned to a raster, this is what it would look like. We have both raster and vector overlaid upon each other here, so we can actually see the differences. Alright, so you see wherever the line, let's assume it's a river, occurred, the entire cell has to be assigned a value. And note that does not represent the shape or the size of the feature very well. Okay, so continuing, so resolution now. So we can increase the accuracy of spatial features, so those would be the features on our maps, by increasing the resolution, or in other words your ability to see details on the raster data that makes the cell dimension smaller. Which makes the cell dimension smaller? So in other words, remember the rule of thumb, the smaller the cell size is the higher your resolution. Where you have higher resolution, you have greater level of detail and accuracy. So increasing the resolution is often done at the expense of increasing your data storage, because now you have more cells to store, and also processing costs. So you'll need greater processing power on your computers, because now you have a larger amount of data to process. So I believe this diagram should be familiar to you. Sorry, let me go back there. Right, so see, when we talk about resolution, we have three examples of different resolution here. We have our 10 meter, 5 meter and 1 meter. Where you see an increasing number of color representations, that is because you now have, because the cell size has reduced, you now have an increased ability to represent additional information. So here we have one color represented in the 10 meter. In the 5 meter we have two colors represented. That means we have two different data sets that can be identified. And in your 1 meter you have three colors. That means we have an increased level of detail represented here. Right? So this note here is to remind you that resolution here with regards to the diagram increases as you move from 10 meters to 1 meter as the cell size is reduced. Your file size, again, remember, is also increased as your resolution increases. Okay, so we're still talking about the data model here, making sure that we thoroughly understand the characteristics of our raster data model. So we know that the raster data model represents continuous variables very well, and this is where information would be transitional. Okay, so it represents significant changes in value over broad areas. For example, if you're trying to map vegetation type, we know in reality, out in the real world, vegetation type does not change abruptly from one side of a line to another side of a line. In the natural, that change is transitional. The same would apply to soil type and other types of variables. Alright, so in order to represent that transitional change, we say that raster data represents this better than vector data would. So the raster data model may also be used to represent discrete data such as land cover. So discrete data may be, for example, like what we looked at in the previous slide. If you're representing a road or a river, that would be discrete data. Okay, however, the details, the representation has to be appropriately chosen, whether you are choosing to represent rivers, or roads, you would choose to represent that using vector. However, if your need is to show a high level of detail in vegetation type, you would use the raster representation. However, if that level of detail is not important to you, you can represent vegetation types using polygon boundaries. Okay, so remember, vector will represent general information. However, if you want details, especially if those details change transitionally from one location to another, you would use raster. Alright, here on the right we have two raster representations. This map here is an example of the vegetation type, and we can clearly see the only hard boundaries you can see is the base map here, where you see US state boundaries. But on top of that, you actually have raster representation of the different vegetation types. You can see this is your legend here, and if you look at the colors, you can see you actually have no hard boundaries. So those are actually pixels. Okay, here we have another example. So here, let's read the caption. So the raster cell assignment with the mixed landscapes. Alright, upland areas are lighter grays, water are the darker grays. So let's say it's essentially two data types we're looking at here. Alright, we are looking at highland areas, which are the lighter colors, and water, your darker grays. So if we were to look at this one cell here, in this cell we see two things happening. Both data sets occur within this area, so it's a mixed cell. So according to the model of the raster data, we cannot assign more than one value. We would have to make a judgment, and most likely what we would do is we will make a visual assessment here and say, alright, it's mostly light gray, so it's mostly highland areas, so let us assign the value of highland areas. Okay, so that is how this would be applied. Okay, similarly here we have an example of a raster representation of forest cover. This is our legend. Okay, and here we see the various color representations assigned to our grid. The various cells have been assigned values of mixed conifer, Douglas fir, oak savanna, grassland, etc. Those are different vegetation types. Bear in mind, the color representation is the final map representation. What would have happened before is that actual numeric values would have been assigned for each one of these forest types. Okay, alright, so let us continue now and move straight into the raster data structure. So we have different methods that are used to encode the spatial entities or the spatial features for storage and representation in the computer. Alright, we will start first with looking at the simple raster data structure, and so I'm not going to go through this in the slides at this point in a whole lot of detail for you. The details would be for your review, and when you're preparing for your exams. I am going to go straight to the illustrations and charts and walk you through it in some detail. Alright, so this first one is an example of a simple raster data structure. Alright, here we have our raster data model represented, and we have some data visually represented there. Okay, that's the dark or the black filled in cells. Here we see how the computer would encode it, how the computer will store that information. So I want you to follow with me. So the first row, so we know that the raster data layer is made up of a series of rows and columns. So if we look at the first row here, we see that there's nothing there. So the data structure, you can see zeros have been applied to that entire row. If we go to the second row, we see this is different. We see that we have the first 3 cells in that row as 0. If you match it, you will see it matches here, followed by 1, 2, 3, 4, 5 ones. That means something is present there. 1, 2, 3, 4, 5, and then followed by 2 zeros. So you see what you see here should be a mirror representation of what you see here. Now this is a simple representation here. Now what we have on this side here is actually how the data would be organized and stored in the computer. So let's make sure we understand what is going on here. So this first set of numbers in the top line here actually represents the information contained in the data layer, the raster data layer. It tells us that we have 10 rows, 10 columns, and we have the highest value available, highest cell value available to us is a value of 1. So we actually have binary coding going on here. So again, this here should be a mirror representation of what you are seeing here. The only difference is now this would be represented as a text file, and each value is separated by a comma. So this is how it would be stored in the computer, so that the computer can understand the spatial relationships and the spatial organizations of the features, where it can reconstruct this representation on your computer screen to represent your features as a raster data layer. Here we have another example of a simple data structure. So it's essentially the same as the previous slide, except that you now have more data represented here. So if you look at this, you have 10 rows, 10 columns, and your highest value of 3. So if you look at the colors here, you actually see 3 colors represented, right? 1, 2, 3. Again, this here, the assignment of the values would be a mirror representation of what you have here and here. For example, let's look at the first row. 1, 2, 3. We have 3 values of 1, followed by 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 7 here. And again, this here is the stored file in the computer. Again, text file, and you have a mirror representation of what you have represented here. So far it should be pretty simple. So let's continue. So the major problem that we have with regards to the raster data is the storage size, because especially when you have higher resolution, as we said before, you have an increased need for storage. Alright, so the storage size could be a problem, because a value must be represented and stored in every cell. So how do we address this problem? We address this problem by compacting our data, compressing our data to make the file size smaller, yet retaining all the information. So we have 4 methods that we're going to look at briefly. Alright, run length encoding, block coding, chain coding, and quad tree data structure. So this one is our run length encoding. Notice this is a familiar data layer we're looking at here, right? Again, the same arrangement, 10 rows, 10 columns, a highest value of 1. But notice we have organized our data differently. So how are we doing that? Our first row, we have no data present there, so we have values of 0. So here what we're saying is we have 10 rows. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have 10 rows of 0. right? So we have 0 represented 10 times. Let's look at our second row, right? Notice the data they have encoded here, 0, 3. That means then that the first 3 cells have values of 0, 1, 2, 3. Then we have 5 cells with a value of 1, 1, 2, 3, 4, 5, and 2 cells with a value of 0. And if you work through the rest of the rows, row by row, you will see that they match here. So the first digit represents the value, the second digit represents the number of times that value has been assigned. And if you look at the number of characters that you have in this file, the number of characters are far less than the first example we looked at, though it retains the same information. So you're now reducing your data volume. So this is called run length encoding. Right. So the second one we would look at is block coding. So block coding uses a series of square blocks to store your data. So again, we're using the same data layer with the same information, but we're going to store it differently now. So here we represent, I'm looking for my right here is my cursor, right? So this is the data layer represented in raster. Here now we're looking at how we store the values. So if you look at it, you would actually see the same form. There are 3 different colors represented there to represent 3 different blocks. All right, we have the dark gray, we have a light medium gray, and then we have a very light one here, 2 blocks here of 4. All right, and this is how we arrange our information. So here now we arrange our information by block size and coordinates, block size, number of cells, and coordinates. All right, let's try to understand what's going on here. So follow with me with the arrows, right? So this first one we're looking at, we say we have a block size of 1, so that's, in other words, 1 cell, and we have 7 of those 1 cells, and they've given us the location of those 7 cells. So let's see if we can find those 7, I beg your pardon. Let's see if we can find those 7 cells. The first one is located at 4.2, so 4.2 is here. The second one at 8.2, 8.2 is here. The next one at 4.3. So all those numbers, there should be 7 of them. Those are the gray blocks of 1 size, 1 cell size. So that's 1, 2, 3, 4, 5, 6, 7. And they should all match to these coordinates, right? The second one tells us that we have a block size of 4. There are 2 of them, and this is the top left corner coordinate of those 2. So let's find those 4. Let's see, the first one is at coordinate 8, 3. So that is at coordinate 8, 3, right? 8, 3, that's here, right? So, and it's a block made up of 4 cells. So you will see that's this block right here, top left corner coordinate at 8, 3, and then the second one is at 7, 5. So 7, 5 will be located here. So if you look, you should see 4 light gray cells that make up that block. 7, 5 is your top left corner coordinates. And then the last one tells us that this block size is made up of 9 cells. There is 1 block like that, and the top left corner coordinate is 5, 2. So that's your this black block here, and if you count them, you would see it's made up of 9 cells. So this here is an example of our block coding. And again, notice it's the same data, but look how differently it's represented. And again, this one even further reduces the number of characters contained in the file to reduce your storage, yet retaining the details. Chain coding, this is another method. Again, the same data represented on your model here. So So with chain coding, we are defining only the boundary of the entity according to direction. We're also using coordinates. So notice here we see our cells that are of interest to us are only the boundaries. Alright, so let's see how this is organized here. So we have a start and end coordinate, because if it is a chain, because we call it chain coding, if it is a chain, in other words, it's similar to a polygon boundary in the sense that it must begin and end in the same location. So this is the start and end coordinate. Let's find that location. It says it's at 4, 4, 3. That's right here. Right? So it must begin and end here. And here the information is directional. So we start at 4, 3, and then it tells us we are to count 2 cells north and then 4 cells east. So if we're counting, we must count this one. So it's 1, 2, we're moving north, and then 4. So from here we have 1, 2, 3, 4. We moved east 4, then 1 south. So you're following with me here, right? So we move 1 south. From 1 south we go 1 west. One west. This is east. 2 south. 1, 2. No, I beg your pardon, I made a mistake. So as we go from 4 east, it's 1 south, 1 east, 1 south, 1 west, 2 south, 1, 2, 1 west, 1 south, 1 west. So we're back here. 3 north, 1, 2, 3, 1 west, 1 north, and then 1 west, and we're back at our starting point. So again, this is another way of compressing your information and representing the same information for the same file. And then lastly, we have our quad tree representation, and this one may be a little bit more complex than the others. So let's try to understand this one a little better. So you have a map representation here, and as you can see, your various colors and patterns represent different information. Let's try and break this down a little simpler. Right, so we assign our values here, okay, and we assign them in quadrants to try to make sense of it, okay, because the concept behind this representation is that each number or each subsequent number in your assigned value to each cell is supposed to give you information about the root of the data. So say for example we have, okay, so this one is only one value. We're gonna say that this represents let's say it's agricultural land use. We have vegetables growing here, right? But that's all that tells you is growing here. In this quadrant now, we have also represented vegetables, but remember we have different types of vegetables that we can grow. So we want some information here. This plot might tell you, okay, I have I don't know, let's say I have peppers growing here, right? But there are also many other types of peppers that we can have, right? So all of this, let's say, might be peppers. The 3 might represent peppers, but then when we come here and we break it down into smaller cell resolution, notice the cell size is different. We can have more information. So the 3 would represent peppers, the 1 might represent a type of pepper, the 3 might represent some other detail about the pepper. I don't know how you distinguish categories of pepper, maybe level of heat or something. Alright, so I hope you all are getting it at this point, right? So each digit represents a different level of information. So when you look at what we have here, where you have digits of 3, it means that there are 3 levels of information contained in that one cell. So you haven't actually changed the numbers of cells, but by the organization of your cell value assignment, you have now included a lot of information in that one data layer. So this is what the quad tree representation looks like. And this is also another example of data compaction. Okay, so what are the raster data advantages? We know it's a simple data structure when you compare that to the vector. It's easy to analyze and compare to other raster data sets. How do we do that? We do that by conducting mathematical comparisons between the two of them. So we will actually see an example of that on the next slide. Raster data already comes in the form, in an image format. Alright, for example, if it's satellite imagery is already in an image format, which is raster. And then also your modeling applications, meaning you can actually conduct simulation scenarios using this type of data representation, that is raster representation. It is easier to do in raster than it is in vector, right? So your simulation scenarios are easily done in raster compared to vector. So here's an example of how you will do analysis with raster layers. This is what we call map algebra. So we have 2 layers. We have fire hazard and we have flood hazard. Each cell value that has been assigned to the cells in a layer represents a level of fire hazard here or a level of flood hazard here. So 1 would be a level 1, 2 would represent a higher level of the hazard. Now what we would do is we would mathematically relate them to each other. In this case, we want to add them together in order to derive a flood and fire hazard map. When we add them together, for example, here this row here, we have a value here. So we see we add 2 and 1 together to get a total of 3. This cell here would be represented by 2 plus 2 to give us 4, and so on and so on. So your final result here tells us that this particular cell has the highest risk of flood and fire, and then we have other cells here that represent levels of risk. Where you see no value assigned, that is because there was no opportunity to add both fire and flood together, so they remain blank. Alright, so we looked at some advantages of raster data already, but there are also disadvantages. What are some of those disadvantages? Spatial inaccuracy. Remember, we looked at that already. Spatial inaccuracy in terms of size and shape and even location of the feature. They are not accurately represented. So your level of accuracy is really dependent on your cell resolution, that is your cell size. Also, additionally, you are reminded that in order to achieve high resolution, you have to reduce your cell size, and by reducing your cell size you get a larger data layer which needs greater storage. So that's another problem. Large storage requirement, you need large storage requirements even for simple data. Alright, so this is one of the things you have to remember about a raster representation. It usually requires larger data storage than the vector. And also, generally, our general perspective or perception is that maps are based on vector. That's how we tend to imagine it, you know, as points, lines, or polygons, because this is how we tend to see the features of the earth. You don't tend to visualize your maps as a series of cells. So our perception or our instinctive perception of a map is also a disadvantage for using the raster. This here is the final slide that actually does a simple comparison of the characteristics of the raster and vector models, and also some comparisons of data structure. Alright, so I'm not going to go through this with you. This is for your revision purposes. Please take your time and go through these carefully to make sure that you can compare the two. Thank you for joining me for today's lesson. Please proceed to the activity provided in relation to this lesson. Thank you.